Hello everyone, in this video we'll pick up where we left off in section 9.7, which is titled Taylor Polynomials and Approximations. Now that we know the definition for the nth Taylor polynomial and the nth Maclaurin polynomial, we're able to do some examples, right? So the first question says find the Taylor polynomials p sub 0, p sub 1, p sub 2, p sub 3, and p sub 4 for the function f of x equals ln of x centered at x equals to, centered at c equals to 1. Right? So what we need to do here is we use this formula that I've starred. We'll use it for n equals 0, n equals 1, n equals 2, n equals 3, and n equals to 4. Right? And so if we go all the way to n equals to 4, notice we'll need, if for n equals to 4, we need the fourth derivative of f to plug into that formula, right? So I need all the preceding derivatives, and I need the fourth derivative, and I actually need even better, the fourth derivative at c equals 1, right? So first, we know our function is ln of x. So my first derivative is 1 over x. My second derivative, this is really x to the negative 1, my first derivative is, so I get negative x to the negative 2, which is negative 1 over x squared. Now my third derivative is going to be positive 2x to the negative 3, so I get 2 over x cubed. And then my fourth derivative, which is the last one that I need, is going to be negative 6x to the negative 4. In other words, 6 over x to the 4. But again, what do I need for my formula? My formula, I need the derivative. I need f of c, f prime of c. Remember, c is 1, so I need f of 1, f prime of 1, f double prime of 1, f triple prime of 1, and f, the fourth derivative of f at 1, right? So f of 1 is just going to be plugging in 1 to my function, so ln of 1, which is 0. F prime at 1 is going to be 1 over 1, right? Plugging in 1 into my first derivative over here, and I end up with positive 1. F double prime at 1 is going to be negative 1 over 1 squared, in other words, negative 1. F triple prime at 1 is going to be 2 over 1 cubed, or just 2. And the fourth derivative at 1 is going to be 6 over 1 to the fourth, or just 6. Okay, so let's write out the polynomials, right, in the using the formula that I have starred there. All right, so p sub 0, just the first polynomial, p sub 0 of x, according to that, is I just would have f of c, which we said was 1. Right, so f of 1, we can stop there, right, because it's just n equals to 0. So this is just a really simple polynomial, and it's just 0. Right? So in other words, p sub 0 of x is just 0, right? Not a great approximation, but it works. It is a polynomial approximation. So now let's look at p sub 1. Well, according to my formula, it looks like f of 1, because c is 1, plus the first derivative at 1 times x minus 1. So now let's plug in our values. F of 1 we said was 0, plus f prime of 1, which we said was 1, times x minus 1, so I just get x minus 1. Alright, so my second polynomial, that it's a little bit better approximation than the first one, but still not great, is x minus 1. So now let's do my third polynomial, so p sub 2 of x. This one looks like f of 1 plus f prime of 1, x minus 1, plus f double prime of 1 over 2 factorial x minus 1 squared. All right, again, I'm looking at, sorry, I pulled down that formula, but I'm looking at this formula here, and here, if this is my p sub 2, that means n equals to 2, so I stop at the second derivative right here, where I make the cutoff. All right, so now plugging into my values, we already said that f of 1 is 0, f prime of 1 is 1, so this just looks like x minus 1, plus f double prime at 1 is minus 1 over 2 factorial x minus 1 squared. Got plenty of room here. So I end up getting x minus 1 minus 1 over 2, because 2 factorial is just 2, x minus 1 squared. Right? So my second polynomial, or my third polynomial that I'm looking at, but p sub 2 of x is equal to x minus 1 minus 1/2 x minus 1 squared. So that's an even better approximation for my function f of x equals to ln of x. Okay, so now p sub 3 of x. Maybe by now you're starting to see the pattern, but this one would look like f of 0 plus f prime of, sorry, not 0. 1 is what we're sitting at. So times f plus f prime of 1 times x minus 1 plus f double prime of 1 over 2 factorial x minus 1 squared plus f triple prime of 1 over 3 factorial x minus 1 cubed. So f of 0, or f of 1 is 0, f prime of 1 is 1, so I get x minus 1, f double prime at 1 is, and you might notice that I'm actually, I know it's always just going to be the previous one plus this extra term, right? So I know it's always going to, I know I'm going to get this plus that extra term. Save yourself a little time. But if you don't see that, f double prime of 1 we know is, oh, sorry, this is glitching out on me. Oh, come on. There we go. So f prime of 1, f double prime of 1, f prime of 1 is 1, f double prime of 1 is negative 1. This is plus negative 1 over 2 factorial x minus 1 squared plus f double prime, which is 2 over 3 factorial x minus 1 cubed. So x minus 1 minus 1 over 2 x minus 1 squared. Again, this is where I was talking about, this is the exact same as that, right? The first two terms are the same. And the only thing that's different is going to be 3 factorial, which is 6. So this would be 1 over 3 x minus 1 cubed. So that is what p sub 3 of x is. And finally, I wanted p sub 4 of x. So p sub 4 of x is equal to f prime, or f of 1 plus f prime 1 x minus 1 plus f double prime of 1 over 2 factorial x minus 1 squared plus f triple prime at 1 over 3 factorial x minus 1 cubed plus, finally, the fourth derivative of f at 1 over 4 factorial x minus 1 to the 4th power. So, using that pattern before, I know it's going to be the exact same as my previous one. So x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. And now what is the fourth derivative at 1? That is 6. 4 factorial is going to be 24. So I get that p sub 4 of x is equal to x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed plus, nope, oh, I should have had a minus 6 there. Whoopsie. So I should have minus 6. My fourth derivative is minus 6, so minus 1/4 x minus 1 to the 4th. So those are my Taylor polynomials centered at x equals to 1. The more powers, so this last one is the very best or is the best approximation polynomial. All right, so let's do another one. Find the Maclaurin polynomials at p sub 0, p sub 2, p sub 4, p sub 6 for f of x equals cosine of x. Then use p sub 6 of x to approximate the value of cosine of 0.1. Okay, so Maclaurin means I'm centered at x equals to 0, right? So my function, just like before, we write out the function first, so I get cosine of x. The first derivative is negative sine x. The second derivative is negative cosine x. And the third derivative is positive sine x. And then the fourth derivative is cosine x. So we're back where we started. So after 4, this pattern repeats, but we'll go ahead and write what they all are. The fifth derivative is negative sine x, and the sixth derivative is negative cosine x. Why am I going to 6? Because I said I want the sixth polynomial, which is of degree 6, so I need the sixth derivative. Right? And remember, this, I want all of these values, I want all these derivatives at x equals to 0 because it's a Maclaurin. Right? So in other words, I need f of 0, which would be cosine at 0, which is 1. F prime of 0, which is negative sine at 0, which is 0. F double prime at 0, which is negative cosine at 0, which is negative 1. F triple prime at 0, which is sine at 0, which is 0. And again, this will repeat, right? So I should know without actually doing any work, just because of the periodicness of the derivatives, that the fourth derivative is going to be right here, is going to be 1. The fifth derivative is going to be 0, and the sixth derivative is going to be negative 1, right? Because it's going to keep repeating like that, right? Sine and cosine always have that, because if I do 4 derivatives, then I'm back to where I started, right? The fourth derivative, I'm back to where I started. Okay, so p sub 0 of x, by the formula that's what we showed for Maclaurin, would just be the function value at 0 because we're centered at 0, and what's the function value at 0 is 1, right? So p sub 0 x equals to 1. Not very exciting. Okay, so now skip p sub 1, so now we want to do p sub 2 of x. Well, I'm going to go right and write the formula, so the formula is going to be f of 0 plus f prime, the first derivative at 0, x, plus, remember I don't have to do x minus c because c is 0, plus the second derivative at 0, x squared. So what is f of 0? That's 1. F prime at 0 is 0, so that x term goes away, and then f double prime is negative 1, so I get negative x squared. All right, so p sub 2 of x is equal to 1 minus x squared. So notice all the terms, because the zeros happen at odd derivatives, all the odd terms are going to go away, right? Because of that 0 that would go there, right? So again, when I go p sub 4 of x, the full formula is f of 0 plus f prime at 0x plus f, whoops, and I should have had over 2 factorial, shouldn't I? Screwed up my formula already, right? When I did this f double prime, it should have been over 2 factorial. So this should be 1/2 x squared. So this should be 1/2 x squared. Apologize about that. Okay, so again, now we're back where we left off. So f double prime at 0 over 2 factorial x squared plus f triple prime at 0 over 3 factorial x cubed plus f, the fourth derivative of x at 0 over 4 factorial x to the fourth. But again, since this guy, I know the first derivative and the third derivative are 0, right? Because all the odd derivatives are 0. So really, it's just going to be all the even ones that survive, right? So it looks like 1 minus 1/2 x squared. And now the fourth derivative is positive 1, so plus x plus 1 over 4 factorial x to the fourth. Right, so that's what p sub 4 of x is. And then the last one is p sub 6. And I think you'll believe me now that, like I said, the odds all go away. So this one looks like f of 0, plus now the odd one goes away. So f double prime of 0 over 2 factorial x squared, plus the odd cube one goes away. So f to the fourth derivative at 0 over top of 4 factorial x to the fourth, plus now the sixth derivative at 0 over 6 factorial and x to the sixth. All right, so I got 1 minus 1 over 2x squared plus 1 over 4 factorial x to the fourth. Now what's this? The sixth derivative we know should be negative 1 because the periodicity of this. So 1 over 6 factorial x to the sixth. Right. So in example 4 here, the Maclaurin polynomials have only the even powers of x. Right? Similarly, the Maclaurin polynomials have only the odd power of x. Generally, this is not true for polynomials that are not that are expanded about a value other than 0. Right? So why does that happen? Well, at the value 0, cosine is 1, sine is 0, and so that's why we have that behavior, right? Because then when I end up taking the derivatives, whether it's sine or cosine, I know that every other derivative is going to be 0. But if I have sine or cosine centered at some other value, I'm not going to have that because other values don't have 0 for sine and 0 for sine and 1 for cosine, right? So let's look at this example here. Find the third Taylor polynomial for f of x equals to sine of x expanded at c equals pi over 6. So Taylor, because it's centered at a different value, and we want the third, right? So I need 3 derivatives. So f of x equals to sine x, f prime of x equals to cosine x, f double prime of x equals to negative sine x, and then finally f triple prime of x equals to negative cosine of x. All right, so now I need these derivatives at pi over 6. All right, so I need f at pi over 6. So I need sine at pi over 6, which is 1/2. Now I need f prime at pi over 6, which is cosine at pi over 6, which is radical 3 over 2. And now I need f double prime at pi over 6, which is negative sine at pi over 6, so that's just going to be negative 1/2. And then the third derivative at pi over 6, negative cosine at pi over 6, which is negative radical 3 over 2. Okay, so I want the third polynomial. So what do? I do p sub 3 of x would be f of, where we centered at, pi over 6, plus f prime at pi over 6, x minus pi over 6, plus f double prime pi over 6 over 2 factorial x minus pi over 6 squared. And I think we can squeeze this in here if I scoot it over. And then plus f triple prime of pi over 6 over 3 factorial x minus pi over 6 cubed. Right, in general, that's what it is. But now we found all these values. Right, so let's plug them in. F of pi of 6 is 1/2 plus f prime, which is going to be radical 3 over 2, plus f double prime, which is going to be negative 1/2. So we'll just read it. Negative 1/2 over 2 factorial x minus pi over 6 squared. F double prime is going to be negative radical 3 over 2 over 3 factorial x minus pi over 6 cubed. So unfortunately this doesn't get a whole lot prettier, so I get 1/2 plus radical 3 over 2 x minus pi over 6 minus 1/4 x minus pi over 6 squared plus, actually it'd be minus here, minus, we'll just leave this as radical 3 over 2 times 3 factorial x minus pi over 6 cubed. So this is our ugly polynomial, but it is a polynomial because it's just powers of x being added up. And so this is going to give us a good estimation for sine of x. Okay, so two things to keep in mind when using Taylor or Maclaurin polynomials for approximating values. First thing we should notice is the approximation is usually better for higher degree Taylor or Maclaurin polynomials. Right? So for example here, I think I actually forgot to do this. For example 4 here, it says use this to approximate cosine of 0.1. So when I say use this to approximate the value, I can go use my polynomial, which is p sub 6 of 0, or p sub 6, and I want to use that to approximate cosine of 0.1. So in other words, I'm going to plug 0.1 into my polynomial, 1 minus 2 over 0.1 squared plus 1 over 4 factorial over 0.1 to the 4th minus 1 over 6 factorial, 0.1 to the 6th. And that's going to give me this approximation 0.995004165. Now the actual value is cosine of 0.1. If you plug that in a calculator, that is really, really close. I don't have it off the top of my head, but it's very, very close. So what I'm saying here by this, I went off a little tangent, but what I'm saying here by bullet point number 1 is if I plugged in 0.1 into p of 4, or if I plugged in 0.1 into p of 0 is just 1, right? This is the p sub 6 is it's a number that's a little bit less than 1, but it's going to be a better approximation than just 1, right? So the higher degree polynomial I go, the better my approximation is for the exact value of whatever I'm trying to find, right? In this case, my function was cosine, and if I want to find the exact value of cosine, I'd plug it into there. The other thing to notice, or the other thing to take note of, is that the approximation is usually better for x values closer to x equals to c, let's just say closer to c, than x values farther from c. So for example here, I centered this guy at pi over 6, right? So what does that mean? That means if I wanted to find, remember this is approximation for f of x equals sine of x. So if I wanted to find, say, an approximation using this polynomial, it would be a really good approximation if I were looking at pi over 5 or even pi over 7, right? If I looked at p P3 of pi over 5, that's going to give me a pretty good approximation. And P3 at pi over 7, that's going to give me a pretty good approximation because pi over 5 and pi over 7 are really close to x or pi over 6. However, if I wanted to approximate P of, say, 0 or -5, that wouldn't be a really good approximation because this guy, this whole thing, this third degree polynomial, this P sub 3, was centered around pi over 6. So it's not really that good if it's not centered around pi over 6. Just think back to this example here at the very beginning when I was looking at e to the x and its two polynomials that we used, right? If I pick an x value that's really close to 0, look, the green, the blue, and the red are all really close to each other, right around 0. Even if I put 0.1 or 0.5 even, right? They're pretty close. Not great, but pretty close. But if I start and I pick, say, -5, if I pick the x value at -5, the actual value, the red part, is going to be really close to 0. But if I plug in a green function, I'm going to have some really big value, like almost, what if I plugged in -5? I'd have almost like 10. And I would have all the way down here to almost -4, right? Not anywhere close to 0. So it only really works if I'm really close to the value that I'm centered upon. So Taylor polynomials and Maclaurin polynomials work really well. They're good approximations. The higher the polynomial is, the higher the degree, and the closer the value it is centered at is to the x value you're trying to make an estimate for. Okay, we'll go ahead and end this video here, and we'll pick up with subsection 3 in the next video.